Okay, welcome back to the afternoon session. Our next speaker is Caterina Doglioni, who will tell us about real-time analysis at the LHC, how to make the most of LHC data.
Thank you very much for the invitation. I'm very happy to speak here, also because a lot of what I'm talking about here has been done at Lundmark in the end. So the papers that we got out are thanks to Lundmark as well. So I will bring you on a short tour of a circle being an accelerator of particles. It's a circular accelerator where we collide protons to discover potentially new particles. So this is the Large Hadron Collider, and I will show you a little bit about the experiments as well. Then I will go into detail about the experiment trigger system, because since we cannot record all the data, we have to decide which one we want to take and which one we don't want to take. And the system that does this selection is called trigger. And this is obviously not the optimal solution. If you could, you would take all the data. You would just record all the data and then look at it afterwards. So how can you make the most of the data in limited circumstances? And this is the answer to this, at least from a number of people in the collaborations, is real-time analysis. I will show you one example of a measurement with using this technique. And then the last part is possibilities for crosstalk in real-time analysis beyond the LHC or high-energy physics. So let's see an introduction about the LHC. This is the Large Hadron Collider. This is not overground, it's underground. It's 27 kilometers of diameter, an accelerator of particles. It collides protons, and the collisions are recorded and analyzed in 4 experiments that are CMS and LHCb and Atlas and Alice. And the Lund is in Atlas and Alice. We've just finished taking data for the first period, and we will take data again in 2021, roughly. To give you a sense of scale, here's how big things are. So this is if you put the Large Hadron Collider around Lund, it would contain the entire city. So you'd have to dig a tunnel around the ring road and then collide particles there. And the detector and the experiment that I work on is called Atlas, and it's about half the size of the Notre Dame Cathedral in Paris. So it's very large. Now for a short video about LHC collisions and data selection. So we'll look at the first part now. So animations are always better than not. And no music. So I can narrate. So this is Geneva. So you see the Lake of Geneva. This is the airport. And this is in scale. It's like a runway, essentially. So this is the accelerator of 27 kilometers. And you see the protons that are circulating in there. And in the 4 experiments, the particles that are accelerated to close to the speed of light collide. And then the experiments, these detectors, record the output of these collisions. And there's a really big number of protons and a big number of turns per second because they really go fast. This is the messy things they produce out of the collision. And there's 600 million collisions every second. Okay, so we'll see where the data goes eventually. Now we need a volunteer here because someone needs to help me find the Higgs boson. I don't know, we can call our study director. You need to find the Higgs boson. It's the heaviest particle in here.
Okay.
Well, someone had dolphins this morning, so I thought of bringing plush toys of particles. You found the Higgs boson, great.
Yes, I like it, yeah.
So what you deserve now is a Nobel Prize. You found it a bit late. That's different particles, yes,
okay.
but that's a W. Anyway, the Higgs boson is a particle that doesn't look like this. It's an elementary particle, so it's not technically not dimensional, but it's what awarded Peter Higgs and François Englert the Nobel Prize in 2013. This was theorized in the 60s, and then it took a very long time to find it. But why? Couldn't we find it earlier? Well, there's a number of things that need to be there for a discovery. Sorry about the fonts. I'm usually a font enthusiast, but I didn't have the right one installed here, so they don't look really great. Anyway, we can still discover the Higgs boson with wrong fonts, says Fabiola Gianotti, who uses Comic Sans. Anyway, I hope this doesn't go too much around the web. She's great. Okay, so what do we need for a discovery? We need a particle collider. Got it. We need 600,000 collisions per second because finding this particle in the bag of other particles that I don't know where it's gone now Oh, okay. Yeah. So there's a lot more other particles than Higgs particles. So only 1 in 10 to the 13 may contain one of these guys, a Higgs boson. Then we need to precisely measure the particles, and the Higgs boson decays into 2 other particles that are called photons. That's an electron. I need a couple of photons there. No, that's a muon. No, it's a neutron. Okay. Yeah. Okay, so 2 photons. So the Higgs boson is a particle that is unstable, so it will not live very long, and it will decay into these 2 photons. And these 2 photons have to make somehow up for conservation of energy, the energy that the Higgs boson had. So you can connect the energy of the 2 photons to the energy of the Higgs boson. And in particular, because E equals mc squared, then you can connect the mass of the Higgs boson to the invariant mass of the 2 photons. But we need to measure all these things, so we need detectors. And these detectors are, one is the Atlas detector, the really large experiment that I showed you before. Then there's also the CMS detector, and there's other experiments at CERN as well. And each of these detectors has millions of readout channels. So you need a lot of people that can operate the detector correctly, not break anything, that can reconstruct and calibrate the particles and do the data analysis. So this is how a Higgs boson has started looking like. This is a histogram. I'm pretty sure that everyone is familiar with that, but if not, this is on the x-axis is the energy of the 2 photons, and the y-axis is how many of these events you have. And you see that you start seeing some sort of bump, and that bump is your signal, and that smooth distribution there is your background. And that bump is in correspondence of the Higgs boson mass. So by measuring the 2 photons, you can actually measure you can actually discover a Higgs boson with a certain mass. And that was the discovery of a boson, and a lot of work has gone into determining that it was the Higgs boson, not just this plot. Now let's go into a short interlude in what we actually want from an accelerator. We want data. And we want very high energy, and we call it the center of mass energy, because with more energy you can discover more massive particles. Again, E equals mc squared. And there's another quantity that is called the luminosity, so how bright our accelerator is, and how much data is collected. This is proportional to the number of collisions. So you want many collisions at a time. You don't collide 1 proton at a time with another proton because it's really hard. They're really small. So you want to collide many protons, and more data means more chances to see rare processes. This is challenging because in order to find the Higgs boson, we needed to collide the protons at 30 megahertz or 40, but it's essentially every 25 nanoseconds you have a collision. So your detectors need to process all these collisions before they get too much other collisions piling up. So you need fast electronic and good buffering to keep whatever you've not processed right away. And then there's 2,800 bunches of protons per proton beam. Each of the proton beam is each of the proton bunches has 10 to the 11 protons, and this is what leads you to 600 million proton-proton collision per second. The consequence is also that you have many of them are simultaneous, like even within your 25 nanoseconds, you are colliding 2,000 protons at a time, so you expect like 20, 30, I don't know, are going to collide at the same time. And you need to distinguish particles coming from each of them. This is why we build such complicated instruments with more than 100 million electronic channels. And we have many sub-detectors, so these are all the parts of the Atlas detector that are used to measure the particle properties. And in particular, Lund built one of the pieces, designed and built one of the pieces together with other institutes. This information is combined in a process that we call reconstruction. And then once we have the reconstructed events, we can count the number of photons and their energy, so we can find the Higgs boson. So who are the people that do this? So these are the experimental collaborations. These are monster experiments compared to the norm. Atlas has more than 3,000 people on. So when we write a paper, we have a very long author list, sometimes longer than the paper. And that makes some people laugh, but if you understand the complexity of the problem and how big of an experiment we need to see very, very small particles, then it makes sense. So how and why we select interesting data? Because we can't record all of it. So we have up to 30 million collisions per second, 1.5 megabytes per collision. Multiply that, you get to 30 terabytes per second, multiply by the time that the LHC is running, roughly. And then you get to order 0.05 zettabyte per year. Oh, sure, but it's not Facebook. Well, in 2014, Facebook was smaller, but now it's bigger. But there's always a bigger fish. There's always someone who is dealing with more data than you, but they usually have more money. So it's really important to have cost-effective solutions for scientific instruments, because how much data you can get means that you can do more discoveries. So we need to select the events that are interesting out of what we can't record in real time. And real time is about milli or microseconds here. So let's have a short video of the LHC trigger systems now. It should start where we left off earlier. So we decided that we can only take one in a million collisions. Only 1 in a million is containing a Higgs boson. It's interesting. So we go for first a fast electronic preselection. So these are FPGAs usually. And then this makes a selection, and they pass the event that are interesting to a farm. It's called a trigger farm. These are cores, just computers. And they make another 2 orders of magnitude the selection of the events that then at this point we are able to record on disk. So we are throwing away 99% of our data. And maybe it's not a great idea if you hear it like that. It's a waste of money. To an extent, yes, but a lot of the collisions will not produce anything super interesting. So there is also a reason why we don't want to take all the data. I'll show you why we want to take some of it. And so this is the trigger and data acquisition chain summarized. You have the collision, you have the detector, then you have the system that makes the decision. Then you have the offline side, where once you've selected the events, you can record it on disk and do your reconstruction, your calibration of the objects, and the data analysis. And computing is essential pretty much everywhere. So we go from 30 megahertz to 100 kilohertz to 1 kilohertz. So at the end, we can take 1,000 events per second to disk, roughly. So what is real-time analysis at the LHC? There's a debatable definition here, because the engineers in the room will horrify of the fact that I'm speaking about real-time. This is something I understood at the AIML meeting when we discussed about this. So this is not hard real-time like you would need in architectures. This is the concept of having a first-pass data analysis that you do on very short time scale with limited information that can influence further data taking. So you just have limited resources and limited time. You have to make a decision. So what's interesting here? So this is a physics plot. I hope it doesn't scare anyone. But on the y-axis is what we call the cross-section. So it's proportional to the frequency of a process. So higher cross-section happens more frequently. Lower cross-section happens less frequently. And then on the x-axis is the particle energy or mass. And it's intuitive to think that processes that have a lower energy happen more often than processes with high energy. And so there's processes that an experiment that is called LHCb is interested in, but they're way beyond this 1,000 events per second. So if you want to take all your signal, then you are actually not able to do that. You have to discard some of your signal, because what is interesting for you happens at a higher rate with respect to what you can take. And also the definition of interesting changes experiment by experiment. So we said that the Higgs boson is down here. So we can't take all the Higgs bosons, but for example, I really like these things called jets. I'll explain what they are. And we can't take all the jets. We have to discard some of them. So if I have a signal process that looks like jets, for example, a new particle that is kind of like the Higgs boson, but not exactly the same, that decays into 2 jets, then I will probably be discarding that signal as well, together with all my other jets. So this is a rare signal process that is buried in a high-rate background, and it has to be discarded. So here we have a menu, and here in the room there's Will Calder, and one of the people responsible for this menu, where you can decide what to have for dinner in terms of Atlas data. And for example, you have to decide how many electrons you're going to take, how many photons you're going to take, what energy they will have. And it's pretty much predefined at this point. Also because you don't want to change things too quickly once the LHC is running. But this kind of thinking presents a risk. Maybe you're not recording enough events of what you should. Maybe you're missing a class of events because you've decided in advance what you wanted to find based on theory, and what nature is giving us is not theorized yet. So there's motivations for making the most of the data. And the motivations are also looking into the fundamentals of particle physics. We have a theory that's called the Standard Model that describes all the particles that we think are fundamental. Fundamental meaning not that they're more important than others, but just that they are, that we can't break them anymore so far. And it has problems like the an aesthetic reason, so it doesn't really look good. The measured Higgs mass doesn't really coincide with what the theory, if you let it run free, will give you. That theoretical mass is a lot bigger than what we see in the theory. You could also fine-tune it. You could add terms to the theory that bring this down, but is that natural? This is one of the problems that people have with this theory. There's also empirical problems, that there are things that astronomy sees that we don't explain. Dark matter is one of them. And I will explain a bit more about that later. So this makes us think that the standard model may be a low energy approximation of a more complete theory. So how to find the hints of the next thing? Well, we have theorists, and the theorists that are there can explain these shortcomings, but so far none of this is favored by data. So they predict very different things in the detector. Either things that are buried in high-rate backgrounds that we might be discarding with the backgrounds, or could be something that is rare and is unusual, and we're not taking that because we haven't thought about that yet. So making the most of the data means that we are enabling discovery. So it's quite important to ensure that these events of all categories that are interesting for us are recorded and analyzed. So it's an interesting time for high-energy physics. I'm sure that you've read the articles about it, that we don't know what to expect from new physics. In the past, we always had a path. We know that there should be new physics somewhere, but we don't know exactly where we're going to find the new physics. And the opportunity is now, because now we have the LHC running. Once it's over, it's over. The data we discard is gone forever. So what we do is three things. The first is to analyze as much data as possible, as fast as possible, and this is the part that I will talk about, is the real-time analysis part. We can also take the data but not reconstruct it right away. If we have the resources, we just park it away. So that's another thing that we could do. Or we could also use machine learning to use algorithms that look for the unexpected. So these are classes of anomaly detection algorithms. I'm not really covering this here, but there's a number of talks and there's a lot of activities in these kind of things. I'll instead go into a use case here, and the use case is the dark matter mediator searches that we do here in Lund. So what's dark matter? Well, there's a lot of people that are a lot more qualified than me to say what it is. I look for it. There's about 85% of the matter content in the universe that we don't know what it is. It's not included in the standard model. Maybe it's not a particle, but if it's a particle, it's not a particle we know. So this is that slice of the pie here, that pie there. And you can see an explanation for that, the structure of the universe, the large-scale structure of the universe, in a nice seminar by Oscar, actually, that I found on the web. So it's a problem. We don't know what a lot of our universe is made of, and we're looking for it. So we work on the assumption that it's a particle because it's a particle collider that we have, and we try to explore that hypothesis. And we try to recreate dark matter in the lab by colliding known particles. So if there is an interaction that connects the standard model world, our world, with the dark matter world, then we should be able to produce dark matter particles. This already presents challenges because if we've not seen it so far, then it means that these processes are very rare. So it could be that we just have to collect more data. The second problem, that many other processes look the same, so these are our backgrounds. And the third problem, that we don't know how these processes look like. We don't know this is a hypothesis, but maybe there's more. Maybe the dark matter presents itself in different particles that we haven't thought about. So we have to make some more hypotheses here, spherical cow speaking like. And we go into a simple hypothesis, hoping that, like in the standard model, we found the most common particles first, so that the electron was discovered first, and that's part of everyday life. We could find the most dominant components of dark matter first, or particles related to this. So thinking about the force, if there's a force, there's usually a particle that mediates that force, and that's the mediator there. And this mediator, because it has been produced from standard model particles, because we produce it at the LHC, we should also see it in standard model particles, as well as in dark matter particles. And the problem for this is that this kind of processes here is exactly of the kind that is buried in high-rate backgrounds that we could be discarding. And this is another plot of this cross-section quantity that I was talking about. So the rate of the events that are the backgrounds are up there, while the rate of the signals we were looking at are down here. So there's orders and orders of magnitude difference. And they look the same, so you can't say I'm looking for some characteristics of the event above that distinguish them from the event below. They actually look the same. And this is when this is what the signal would be. It would look like a bit of a Higgs boson like signal on top of a background, and the background is a lot bigger than the signal. And you hope that with this you can discover this mediator of dark matter. The problem is that because of these large backgrounds, we're actually discarding most of the data. So we're discarding both the signal and the background. So this is what we would like to have, and this is the actual recorded events that we are allowed to have because we don't have all the possible bandwidth we want at the LHC. And if you're doing a statistical analysis, it makes a huge difference if you have 100 events with weight 1 or one event with weight 100. And we're in the second case so far. And this means that there's a part of this is the parameter space for this kind of models. On the y-axis, it's something that is, again, connected to the rate of the events, and the x-axis is the mass of the events. There's a region here that no one's looked into before because all these experiments here are over, and the LHC is just starting over here. So if no one does anything, then dark matter could be here, and we will never know. So we have to look into that. And doing that means that we're trying a paradigm change, going from asynchronous data analysis, that you first record the data and then you analyze it, to real-time data analysis, where you reconstruct or analyze the data as soon as it's recorded, and discard the raw data, because that was the thing that occupied the most space. So this is a bit of a technical diagram, but this is the trigger system. So because the trigger system has seen the particles, it knows about the particles that it recorded, so you can take out some information out of that and put it into a special stream. And then you do the analysis with these other objects. And a slightly less technical, intuitive way is you have to take a lot of data in, and you read a lot of data in at the level 1 trigger level. So afterwards, when you take the second level decision, the high-level trigger decision, then you can either store a large amount of data for a small number of events or a small amount of data for a lot of events. And by doing real-time analysis, you're doing the latter. Not always you can do this, because sometimes you need the whole raw data and to go back to it, to reconstruct it again. But a lot of the time you can do with this reduced amount. So I'm sorry, the responsible for these plots has just left the room, but there's this is the Lund University postdoc, Wade Calderon. He's implemented this method together with a team of other people by reducing the event size to 5% of the full event. So you're discarding 95% of the information. You don't use it anyway, so why keep it? And that means that instead of taking the 1 kilohertz, that 1,000 events per second, you can take 20,000 events per second just for this analysis. And this means that you get from this regime here, in which these are a number of events as a function of the mass of the possible new particle. Before, at some point, you had to give up on taking events, and now we don't have to give up taking the events anymore, which can take everything. And most of the data analysis for this plot that went on physics review letters was done at Lundmark. And this is actually closing the gap at low masses, as I was showing before, in the plot that I was showing before. So before, we just had the purple curve, and now we have a lot of different other curves that are looking into that region. Unfortunately, no discovery yet, but who knows where dark matter is. So in the last 5 minutes, I wanted to give you a feeling of how real-time analysis can go beyond particle physics. So this is a slide that I've taken from a workshop on real-time analysis where there were many talks from astronomy and astrophysics. And I saw a parallel from a slide that I'd seen already in a high-energy physics experiment. There's the LHC and modern surveys, galactic surveys, are actually fire hoses of data. What do you want to do with this data? Just get overwhelmed with it? Probably not. But there are challenges that are common, because, for example, LSST, so it's a survey that could inform other instruments of where to point, because it's a very fast, lots of data on where interesting things happen in the sky. So you could spot interesting events with this, with the LSST. Then you trigger a follow-up with another instrument, for example, a more precise telescope. But this other precise telescope can't just follow everything that is interesting. It has a limited resource, and it's time. And if one doesn't follow up right, then there's missing information for the interesting transient. That's a similar problem at the LHC. because you spot the interesting event, then you want to record the event, but you can't. And if you don't record the event, you lose the event, and it costs a lot of money to recreate because you have to build another LHC. So there's possibilities for crosstalks in collaborative environments, and this is something that has started from high energy physics, but it's being discussed also in other contexts. So one is the High Energy Physics Software Foundation. It's mostly about software, but there's also the trigger component here, where it's a forum for physicists with interest in software, and it's, if you know about the IRIS-HEP effort at the NSF, so it's the first institute of computing for high energy physics built in the US. This was what sort of built it. And there's also another thing that is called dark machines. This is a collective, somehow less organized, more bottom-up. It's astro and particle physicists interested in machine learning tools for dark matter. And this is mostly self-organized efforts, and that's why it's fun, because a lot of people start working together and deciding what to do. So these are places where people can discuss these kind of problems. It can also go beyond academia, because it's the big data analysis and the fact that the data is cheap to collect but expensive to analyze is a common problem. So there's tools that we can share, so machine learning, hybrid computer architectures, and the connections are to IT, Internet of Things. We have a lot of data, but if you don't say anything about that data, your mail goes off and you don't know about it in your fridge. That's Internet of Things for me. Well, not yet. I think that someone said, I want to machine learn a toaster in this room. That was in one of the compute seminar, was the best option, the best example of this. But in general, time to insight is the key metric for a lot of applications of this kind of techniques. And so there's a number of networks that have either started or are starting that connect different fields. And there's one proposal that we put together where also some people in the room were involved in discussion. That we will see if that is something that goes through or not. But still, there's people that could be interested in working together. So as a conclusion, we know the future of computing is not as rosy as Moore's law, because things are not getting cheaper fast enough for us. So the data rate is growing, but the decrease of cost is not growing fast enough, if you see what I mean. So we don't know what the future is going to bring. Maybe there is a breakthrough. There's a breakthrough discovery or something, but in 2012, for example, the decrease of cost to CPU was 33%, and now we're going to like 20%, and then maybe it's even less. And the cost of storage as well, it's not decreasing a lot. So facing this moderate improvement, you could start thinking about a different analysis technique where you don't need to analyze all the data right away. You can take a smaller amount of data and be more economical. And the other thing that I wanted to leave you with is that discoveries are not really in real time. So the Higgs boson is the particle that has taken the longest time to be discovered. So this is the years from concept to discovery, and those are the different particles. And the Higgs boson has a really huge bar from the 60s to 2012. So one takes large instruments and time to make discoveries, even with all the techniques that we have. So finally, we aren't done taking LHC data. We still have to take 10 times more data. So we have looked at the low-hanging fruit. So if people say, well, the LHC hasn't found anything now, they will not find anything in the next 10 years. Well, I don't believe that, because low-hanging fruit can come and hit you in the eye. So probing for new physics at the scale that is quite important for the standard model, so that's the electroweak scale, is important, because that's where the standard model particles are located. So maybe there's more particles, just more rare. But to do this, you need efficient trigger systems and new data taking techniques. And then finally, real-time analysis and decision-making crosses fields. So this is a place where we can really think together and collaborate. So thanks on behalf of all of us and more.
Okay, questions for Caterina? Ross?
So what sorts of things can you do sufficiently quickly to have them in the loop, as it were, in your system where you analyze a fraction of the data online? And what sorts of things are currently too computationally expensive to do in that loop?
It's a very good question. So it's, for example, we have different detectors. So I'm going to start with the things that we cannot do, because that's the thing we wish to do first. So we have different parts of the detectors that do different things. So the tracking detectors look at the track of the particles. And this is a combinatorics problem that is quite difficult to solve, right? If you take a lot of space points from all that spam of particles, then it will take too long to be able to reconstruct the tracks of the particles. So you don't have that kind of information. And that's not great, because when you find a new particle, you want to follow it through all the parts of your detector. So that's why we're building a different system that, instead of doing the reconstruction of all the possible tracks, it just pattern matches. So it's like a lookup table. It finds 3 points that look fairly similar to a pattern, and then it matches them, and that's a lot faster. So this could be a solution to that. In terms of things that we can do, is that we can do a lot for this object that we call jets. We can do a lot. For photons, for example, we would need this tracking information to do something better with this kind of technique.
Okay, any further questions? Yep.
When you usually have, how long it takes, what is the period, for example, to like imply some changes on the triggering system and all this real-time analysis?
I wish Will was there. Yeah. It could take, in principle, it could take no time. You could just go there and make a change in the code, commit it. It's all the code is public, and essentially everyone can do it. But you want to be careful with that. So the time that it takes is not just the time that it takes to just make the change. It's a time to validate the change and make sure that it's all good. And it's not going to, for example, introduce other problems or other bugs in other people's data taking. So that's why it takes, when you want a change, it usually takes, I would say, like a month to make a change with respect to what you decided, if you want to implement a new thing or a new selection. But now we have 2 years of shutdown, so the LHC is not taking data, and that's why we're working mostly on software and mostly on the changes that we want to make. So we test them on simulation, and we're ready whenever we start again.
Yeah, Philip.
A slightly different question. In the LHC, what is the ratio of energy usage between generating the particle collisions to the complete energy cost of the data analysis?
That's a very interesting question. I actually don't know the numbers, really. I think that still powering up the LHC is quite a significant part of that cost. And the data analysis, mostly the cooling, I have the feeling it's less. So I mean, we're comparing a lot of magnets versus a farm. But then you could, I don't know, maybe Oksana has thought about this. Like if you sum up the computing power of all the computing grid, I think the LHC wins at that point.
Okay. So while Nikolai is setting up, I'll ask a final question for you. So as an astrophysicist, we sometimes hear a little bit of rumors that supersymmetry is looking less and less likely as an explanation for dark matter. What is your take on this?
I think that's the low-hanging fruit that hits you in the eye kind of problem. So yes, the natural supersymmetry, the thing that you would think solve all the problems at once, is not an easy target. It's not something that we've discovered yet. At the same time, supersymmetry with particles that have characteristics that would fit dark matter, there's still a lot of models, just more rare or more difficult to find. So I think it's just a wait and see kind of answer.
Okay, then let's thank Caterina again.